Okay, everyone, 12.4, tangent vectors and normal vectors, which actually has quite a bit of application, but we'll get to that later. So this all stems from an idea that you learned about back in Cal 1 when you learned about tangent lines. So to remind you, basically you could find the equation for any line tangent to a graph on the XY plane um, using an initial point and the derivative. Remember, the derivative was what gave you the slope of that tangent line, and the initial point is what allowed you to write the equation of the tangent line. All right, so we have something similar when we talk about vector valued functions, except instead of talking about a tangent line, which we can and we will in one of the examples, um, we talk about a tangent vector, right? So we have a tangent vector, we have a normal vector, right? And just FYI, normal again just means perpendicular. In this case, a normal vector would be perpendicular to the tangent vector. And remember conceptually, if I had to draw a little graph here, like let's say this is our function. Remember your tangent line touches at exactly one point on the function and kind of just keeps that exact slope going in both directions. Similarly, the normal line would be the line that passes through this point that is perpendicular to the tangent line. And remember, the way that you calculate slope of a perpendicular line is you flip the fraction, you switch the sign. So with that said, let's look at some examples with vector valued functions. First one, find the unit tangent vector to the curve given by this vector valued function. So keyword here, unit tangent. Typically, when we find the tangent vector, we're only really concerned about the unit tangent vector. Side note, notation-wise, this is usually denoted as T of t, right? T is a vector, so I put the arrow over it, but T of t. And you'll see that in your homework because that's how your textbook um, refers to it. So similar to the tangent line for a two-dimensional function, we have to start by finding the derivative, because remember the derivative gives us the slope, or in this case, the direction of the tangent line. So taking the derivative of r of t, we can go component-wise. Derivative of t is 1, so we get I. Derivative of t squared is 2t, so we get plus 2tj. Now, if I want to know what this is when t is equal to 1, right, all I have to do is substitute the 1 anywhere that I see a t. Since there's no dependence for the I component, that's still going to be I. And this will be 2j, right? Just plugged the 1 in for this t. Other thing, because this is a unit vector, remember we have to divide each of these components by the magnitude. So we need to get the magnitude of our direction vector. Since we're only interested in the case when t is equal to 1, we can just do the magnitude of r prime of 1. Right? If I wanted a general magnitude for any value of t, I could use that same definition with r prime of t. Right? But for this one, we'll make it simple for ourselves. So we take the square root of x component squared, 1 squared, plus y component squared, 2 squared, which will give us the square root of 5. And that means that my final answer, so this is going to be my unit tangent vector when t is equal to 1, is 1 over square root 5i plus 2 over square root 5j. And that is the answer to that question. So looking at the next example, we can actually take this unit tangent vector that we get and use it to write parametric equations for the tangent line. Because remember, when we go to three-dimensional space, we don't just write y equals mx plus b. We have an equation for x, an equation for y, an equation for z, right? And just like when you learned to find the equation of a tangent line in one variable, we can do this with vector valued functions using t. So starting off, we're going to need to find the derivative of r of t. All right, so I know derivative of 2 cosine t is -2 sine t. That's my I component. I know that the derivative of 2 sine of t is 2 cosine of t. So that's my j component. And the derivative of t is 1. So that's my k component. Now that I've got that, I can, yeah, I could go ahead and get the magnitude if I want to, but I'm going to make life a little bit easier. So notice that we want to write out the parametric equations for the tangent line, tangent to this helix at this point. So this point is going to correspond to a specific value of t, right? And just like in the last example, to write out my unit tangent vector, I need to go and figure out what value of t to plug in. Here they gave it to me. Here I have to figure it out. So I could do this using, um, yeah, I could do this using any of these components, all of these components. They should all end up getting me to the same conclusion. So the easy way out is I know what the z coordinate is, and my z coordinate is equal to t. So from that alone, I already know that t is equal to pi over 4. All right. But keep in mind, if I were to plug this into either of these components, what would I get? I would get square root of 2 over 2 multiplied by 2 gives me that coordinate. Similar thing, sine of pi over 4 gives me root 2 over 2 times 2 gives me the y coordinate. So no matter which of these components I used, I ended up getting the same value of t. All right. So now that I know what the value of t is, I can find my derivative, r prime, when t is equal to pi over 4. So I end up getting -2 times sine of pi over 4 I plus 2 cosine of pi over 4 j plus k. No dependence on t for this one. And knowing my unit circle, I know that this will work out to negative square root of 2i plus square root of 2j plus k. And remember, for me to get my unit tangent vector t of t, I need to divide all of these components by the magnitude. Okay, so to find my magnitude, I'm just going to take each of these components and use them in the formula that we know to find magnitude. So if I square this, first off, it'll be positive. But if I square the square root of 2, what do I get? I get just 2. Same thing here. If I square this, I end up getting 2. And if I square 1, I get 1, which means that our magnitude is the square root of 5. If you're clever, you could actually figure out that the magnitude for r prime is the square root of 5 for all values of t. It involves a trig identity. Pretty fun. Anyway, now that we've got everything we need, I can actually write out what t of pi over 4 is. All right, that's going to be 1 over the square root of 5 multiplied by basically this guy. So negative square root 2i plus the square root of 2j plus k. All right, and at this point we have our unit tangent vector, okay? And we can actually use it to give us the slopes in each of the parametric equations. Combine that with the fact that we are given an initial coordinate that tells us a starting value for x, y, and z, and it's pretty simple. So x, we're going to look at the x coordinate, square root 2, plus, actually minus the square root of 2t, right? And I get that from this. Notice this is the number that's used when I actually have that magnitude factored out. But as we know with parametric equations, there's typically more than one way for us to write them, especially because if you plug in different values of t, you'll still end up getting the same points as long as your methodology is right. So if you were to write minus the square root of 2 over the square root of 5t, that would still work. Right? It's just you would have to plug in different values of t to go from one point to another, right? But it still would map out the exact same points on that line. Right? This just is easier to work with. Okay. And then we can do a similar thing with y. We look at our y coordinate, square root 2, look at our slope from the j component of my tangent vector, so plus the square root of 2t. And that's the equation for y. Now for z, look at your z coordinate, pi over 4, plus, and then you look at the component for k, you get 1, so plus t. And there we go. So these are the parametric equations for the tangent line. And that's basically how you find a tangent line for vector valued functions in 3 dimensions, right? You get your tangent vector, which is the equivalent of getting the slope in Cal 1, right? Derivative, plug number in, derivative, plug number in. And then you basically write out parametric equations, which is the equivalent of point slope form in Cal 1 to get your equation. All right. So these two examples have focused entirely on finding tangent vectors and using tangent vectors to write equations for tangent lines. But this section also covers normal vectors, which are important for the applications that we're going to see, right? So to remind you, the process for getting a normal line in Cal 1 would have been getting the derivative, plugging a number in, that gives you the slope of the tangent line. Then to get the slope of the normal line, you'd have to flip and switch, right? So flip the fraction, switch the sign. That would be the slope for the normal line. Then after that, you could use point slope form, knowing the point that the normal line has to pass through to write out the equation of the normal line, right? So kind of following similar analogs, we can figure out we would need to figure out essentially a vector that is perpendicular to the tangent vector. Here's the problem though. In 2 dimensions, that's easy. In 3 dimensions, there are literally infinitely many vectors that are perpendicular to my tangent vector. Right? Case in point, if this is my tangent vector, right? This is perpendicular. This is perpendicular, this is perpendicular, that's perpendicular. Going directly under, that would be perpendicular, right? Anything that's in the plane that kind of makes a 90-degree angle with this line is going to be perpendicular to this vector. So as a result, we will narrow it down to just one normal vector that everyone refers to when they say, what is the normal vector, right? Specifically, we call it the principal unit normal vector, right? Principal meaning the main one, unit meaning divide by magnitude. Normal vector just means that if you were to take the dot product with the tangent vector, it would be 0 because of orthogonality, perpendicularity-ness. Yeah, words aren't words. All right, but anyway, we can use this formula to find our principal unit normal vector. Right, so that's the one that everyone finds when they find the normal vector. All right, so for this next example, we have a two-dimensional vector valued function, and we want to find the principal unit normal vector as a function of t, and specifically when t is equal to 1. So first thing we need to figure out is t of t, which we can get by starting off with the derivative, r prime of t. So r prime of t, we end up taking these derivatives. Derivative of 3t is just 3, so 3i. Derivative of 2t squared is 4t, so 4tj. That's my derivative. Since I want to find my principal unit normal vector as a function of t, I'm going to actually get the magnitude before plugging in 1. And this is a thing that you can always do if you really, really like it, right? But you don't have to sometimes. So the idea is the same. I'm just using my magnitude formula. The only difference is that I'm going to have t's in my answer, and that's fine because eventually I'm just going to be given a number to plug in for t. All right, so doing that, we'll square the I component. That's going to be 3 squared. Square the j component, 4t squared. Notice that's in parentheses because the 4 also has to be squared. So when I calculate that, I get 9 plus 16t squared. And that's going to be the magnitude of r prime for any value of t. So I know that for any value of t, my unit tangent vector is going to be 3 over the square root of 9 plus 16t squared. It's my I component. Plus 4t over the square root of 9 plus 16t squared. And that's my j component. So that gives me the unit tangent vector, right? To find my principal unit normal vector, I need to take the derivative of this guy and divide by its magnitude, which looks kind of gross, but it's a good way for us to review some of the derivative rules from Cal 1 that may be long forgotten. So to start off with, you could use the quotient rule for both of these, all right? For derivative of this guy, derivative of this guy. You could also rewrite this so that you can use the chain rule for the I component, but it would be annoying for this one because you would have both a product and a chain. So I'm just going to do quotient rule for both of them. All right. And I have a fun little song for you to remember your quotient rule. F prime g minus f g prime all over g squared. F prime g minus f g prime all over g squared. Yeah. Anyway, listen to that enough and it'll be stuck in your head. Find yourself at the grocery store reciting the quotient rule. That's my goal as your teacher. All right. So when we talk about F and G, F is our top, G is our bottom. So top prime, that would be 0 because 3 is a constant. So F prime G is just 0, nothing there. Minus F G prime, all right? So 3 multiplied by the derivative of this. To remind you, I'm just going to write this out to the side. The square root of 9 plus 16t squared can be written as 9 plus 16t squared, all raised to the 1/2. So if I take the derivative, right, we can do that with our chain rule. So I bring the 1/2 down. Inside does not change. Subtract 1 from the power. And then because that's not just a t, we have to multiply by its derivative. Derivative of 9 is 0. Derivative of 16t squared is 32t. Now, if I multiply this 32 with this 1/2, which I can do because this is not raised to a power, right? I can't do anything with this because that's raised to a power, right? If I multiply the 1/2 and the 32, that's going to give me 16t over, because that's a negative exponent, I can bring this down, the square root of 9 plus 16t squared. So this is the derivative of that square root term. So you have 16t over square root of 9 plus 16t squared. So that's f prime g minus fg prime, and this is going to be all over g squared. If I square that square root, it just becomes the inside of the root. And that's our I component. Then our j component, we can do something similar. So f prime g, so derivative of 4t is 4 times the square root of 9 plus 16t squared minus fg prime. So 4t times the derivative of this, which we already did over here. All over g squared. So that's just 9 plus 16t squared, and this is my j component. So I've got this, so I've got this expression here, and I need to find the magnitude. So my magnitude, remember, we're just going to square all of this. But actually, before I do that, wow. But actually, before I do that, I'm going to simplify this a bit because thinking about squaring this, and yeah, it seems a lot grosser than it actually needs to be. So first thing, I have fractions within fractions. You see that's a fraction in the numerator. That's a fraction in the numerator. I can clear those by multiplying the top and bottom by this denominator. And what's going to end up happening is it's going to make it so that neither of these has a fraction inside of a fraction. So if I look at my I component, first off, if I multiply 3 times 16, I'll get 48. So we have negative 48t. If I multiply the top by this root, then it's going to go away. And in the bottom, we'll have this guy to the 1 times this same guy to the 1/2. So we get 3/2. Now for this one, same thing. We can multiply every term by this root in the numerator and then in the denominator. Yeah. So in the numerator, what's going to happen is since that's already a root, if I multiply it by itself, I get just the inside. So that's pretty convenient. Turns into just 4 times 9 plus 16t squared. Then over here for this term, when I multiply by that root, the fraction goes away and I'm left with 4t times 16t. So minus 4 times 16 is 64t squared. And this is all over, now it's going to be 9 plus 16t squared, all to the 3 halves. That's our j component. This guy can actually be simplified even more in a way that's going to make it turn into something pretty nice. So if I hippity-hoppity distributive property this 4, all right, 4 times 9, I'll get 36. 4 times 16, I'll get 64t squared minus 64t squared. So I don't actually have any more t's in the numerator here. So for my I component, I still have this guy. And for my j component, this is going to simplify to just 36 over this same thing. 9 plus 16t squared to the 3 halves j. Okay. So at this point, when I go to find the magnitude, we're going to get some interesting things happening, right? Because this is to the 3 halves. So I know that when I square this, that's going to go away and it'll just be to the third. So doing that, let's oh, that's not some paper. Hmm. Ah, perfect. All right. So continuing. Okay. We know that the magnitude of t prime of t is going to be equal to the square root of this component squared. So negative 48t over 9 plus 16t squared, all to the 3 halves, right? That's the component. We're going to square that, plus this component also squared. Okay. So then we end up with the square root of, we'll call this 48t in parentheses squared. I lost the negative because when I square a negative, it will be positive, divided by this denominator, but now because power to a power you multiply, it'll only be to the third power. So 9 plus 16t squared to the third power. Then for this one, 36 squared over the same denominator. And that gives us the magnitude. If you wanted to, you could also just put this entire thing as one fraction. Wouldn't really be super helpful, but yeah. So I know that my principal unit normal vector n of t is defined as t prime of t divided by the magnitude of t prime of t. All right, so then we end up getting something interesting here. Actually, you know what? I am going to write this as a fraction. Okay, so bear with me on this fraction part. So we have 48t, all of that squared, plus 36 squared under the square root as our numerator. Remember, when you take the square root of a fraction, it's square root of the top over square root of the bottom. right? So if I wrote all of this as one fraction, this would have been the top. The bottom would have just been this denominator. But notice this is going to end up being 9 plus 16t squared now to the 3 halves, which is what we got earlier. But here's the thing. When we go back to write our unit principal unit normal vector, yep, there we go. We're going to end up having some stuff happen that makes this a little less gross when we look at the final product, especially keeping in mind that we're going to have to plug in a 1 at some point. So remember our simplified components. So we have negative 48t over our denominator divided by this. But remember, if I divide by a fraction, that's the same as multiplying by the reciprocal. And that's our I component. Plus, then we had 36 over our same denominator. Oh, whoops. Forgot to divide by the magnitude. Silly me. All right. So multiply by the reciprocal. Okay. And what you notice about each component is that these guys will divide. So our principal unit normal vector is going to be given by negative 48t over the square root of 48t, all of that squared, plus 36 squared. That's our I component. Plus 36 over that exact same denominator. And that's the J component. So that's my principal unit normal vector. If we wanted to, we could factor out 1 over that denominator, and we would leave behind negative 48ti plus 36j. We can do that. That's a thing. If I wanted to find my principal unit normal vector when t is 1, all I would have to do is plug in 1. So I'd get negative 48 over the square root of 48 squared plus 36 squared. That's your I component, plus 36 over the square root of 48 squared plus 36 squared. That's your J component. And that's the principal unit normal vector when t is 1. And side note, y'all, if you know your Pythagorean triples, that actually becomes something you can do. Because think about it, that's 3 times 12, that's 4 times 12. So the missing side would be 5 times 12, also known as 60. So we could write that as negative 48 over 60i plus 36 over 60j, which really just simplifies to negative 4/5 I plus 3/5 j.